Hi, good morning, afternoon, everyone. Thank you for joining us. It gives me great pleasure to welcome you all to today's webinar organized by Cell Press on emerging memory technology. The future of data storage relies on new technologies that are reshaping the landscape of computing, including MRAM, memristors, phase-change memories, ferroelectric, and spin-texture devices, and other technologies engineered within the back-end of line of conventional silicon CMOS processes. Innovations in device physics, material engineering, and circuit architecture are unlocking new possibilities for faster, more efficient, and intelligent systems. Whether you're a researcher, engineer, or simply curious about next-generation memory, today's discussion will provide cutting-edge insights from top experts in the field. My name is Elisa De Ranieri. I'm the editor-in-chief of Newton, the Cell Press journal dedicated to physics. And along with my colleague, Johnny Wong, who's the mastermind behind the event, but can't unfortunately be here with us today, we're excited to host this discussion and engage with you, the audience. Before we begin, I wanted to highlight that many of the journals at Cell Press publish research related to topics of today's presentation. Of course, Newton, we are very much interested in this area. We launched last year, so I would encourage you to check us out and look at our website, but also more established journals in our portfolio, such as Matter, Device, Cell Reports, Physical Science, and iScience are all interested. You can find links to the latest issues of these journals in the resource panel section. Without further ado, let's get going. We are very much honored to have four distinguished speakers for this panel. Ramamurthy Ramesh, professor at UC Berkeley, Jiwon Kim, associate professor at MIT, Wei Lu, professor at the University of Michigan, and Suman Datta, professor at Georgia Tech. Each will briefly introduce their work, and then we'll proceed with a moderated panel discussion on the latest advances in various memory technologies, focusing on the challenges to overcome. We will then open up the floor for questions from attendees. So if you have questions for any of the speakers, use the Q&A box on the right of your screen. You can enter a question at any time or upvote questions you would like to be answered by clicking on the thumbs up under the question. We will try our best to pass on as many of your questions to the speakers as we can during the Q&A. It is helpful if you include the name of the speaker to whom you would like to direct your question. And finally, at the top right of the screen is an option to turn on closed captioning. Click the CC button and select your preferred language. So now, kicking it off to our first speaker, Ramesh. Thank you very much for joining us today, and please take it away.
Thank you, Elisa. Thank you very much. First, congratulations to you and your team in Newton for a fantastic start. The calculus seems very promising. So onwards to great science and great publications through Newton. I wanted to kind of give you a background since we're leading off this whole discussion. About already 6 years ago in the previous administration, 15 years ago, I had done something called the Sunshot Initiative. We'll show you a slide on this. But in the previous administration, we had written a set of reports for the administration, energy department particularly. But what are the biggest challenges in energy? And that we identified 5, and one of them had to do with CO2 capture. The other one, hydrogen economy. The third one on storage. The fourth one on efficiency in the built environment. For each one of them, we gave targets, cost targets, which were built upon what we learned from the Sunshot Initiative. The fifth one was one which was very intense in our team. The team had about 20 people across the spectrum: policy, finance, technology, science, people like me. And we had intense arguments, and our lead was Arun Majumdar from Stanford. He was saying, computing is not an energy issue. And I was saying, no, it is an energy issue because of exponential growth. And that, sure enough, has been showing up. That's why I have the title of Energy as a Final Frontier for my short presentation. I mentioned Sunshot. Sunshot itself drew inspiration from the Moonshot, which was the Apollo program. Back in the late 50s, early 60s, the United States was under immense pressure because there were other countries which were already farther along in the space program, the Soyuz program, for example. And so this led the Kennedy administration to launch the Moonshot Initiative. And you can read it there at the bottom. And it was basically saying, hey, bring your best ideas, the best engineering science ideas, and go after the big challenge. And the challenge in this case was how to put a man on the moon and bring that person back. Apollo 13 was a better example of that. In any case, this speech was given at Rice University, which is where I was until August of last year. And so this was the backbone for bringing the nation together. Sunshot derived from this. It was basically talking about harnessing the power of the sun for renewable clean energy and so on. And the other 5 topics I mentioned to you, we called them earth shocks because they were really looking at solving the biggest problems in energy on the earth. Okay, so our inspiration comes from Moonshot. We now switch to computing. If you remember, I mentioned a few minutes ago that this was a very intensely debated question. There is no debate now. It is very clear that energy is a very important part, primarily because of the stuff that you see. My colleagues will all speak to greater depth on this. AI is taking off. And frankly, that genie has left the building. There is no way we can capture it. Presidents, kings cannot stop this. But the only thing that can really stop the progress of AI is energy consumption. And so that's an interesting observation. This slide hopefully captures this. This actually has 2 parts, and unfortunately we can't see the background part of it, but that's fine. The foreground of this shows a calculation we did back in 2014, which said that energy consumption in electronics, because of AI, machine learning, IoT, is likely to go up exponentially. And that's been true to form. On the other hand, as Shuman will tell you, we haven't made much progress, quantitative progress, on reducing the energy per bit. It's about a few tenths of picojoules per operation. So our pitch was, can we actually get to attojoule, 10 to the minus 18 joules per operation? If we don't do that, it's very likely, and that's a slide in the background, which is an SRC report, which came in late 2020. About 8% of compute energy, which is electrical energy, which is approximately 20% of primary energy, some fossil fuel kind of energy. So that could be the total energy consumption in computing. And therefore, we have a problem to resolve, how to reduce the energy efficiency. If you go back to history, and this is a slide that my colleague Sashi Manipatruni, who was formerly at Intel, he gave several talks based on this. If you look back at history, you can see this plot, which is a very benign looking plot. Heat output in watts per centimeter squared as a function of year. Bipolar, which these 2 fine gentlemen on top, Shockley and Bardeen, they triggered at Bell Labs. That took off quite a bit in the 60s and 70s, but by early 80s, it had already reached a huge amount of energy consumption. That led to a transition to CMOS, which Gordon Moore, Bob Noyce, and Fairchild, Intel, all of them triggered, but that has the same trajectory. So it's very clear that one needs about 1,000x improvement in energy consumption. And our hypothesis, and this is really part of my own research, what people at Kepler Computing are doing, is that quantum materials, where we don't just use the charge of the electron, but all the quantum mechanical degrees of freedom can be used as a pathway to transform computing. So with that, I'll go to my last slide. And basically, the pitch here is, and you will hear a lot more from Shuman, who's done some fantastic work on this topic as well. The intention is to use physics to drive the innovation. Not just circuit design, but physics to drive the innovation. So this slide on the left, it shows you a nominal CMOS channel. The Boltzmann distribution function controls the energetics of the system. And if you have n particle, let's say it's 1 billion electrons, energy dissipation in this process is maximum of nkt log 2. And the question is, can we get to KT log 2? That would be very interesting. And the hypothesis is that one can use internal correlations, like in a ferromagnet, which is exchange interactions, in a ferroelectric, dipolar interactions, multiferroics, which couple both of them, where you use a double well structure, which is shown on the right side, but you use it not only for storage, but also to do logic in the so-called in-memory compute or logic in memory kind of approach. The biggest thing that, Sashi deserves a lot of credit for this. The biggest thing one can take away is that voltage is a proxy for energy. So there is a big push to reduce energy consumption by reducing the voltage. The question, first order question is, can you get to operating voltages of the order of 100 millivolts? And I will stop there. We'll be very happy to take questions at the end or right now. Sarah, back to you. Elisa, back to you. Sorry.
Thank you so much, Ramesh, for this excellent introduction to our webinar. I would like now to ask Jiwan to introduce himself with a few slides. So please take it away.
Okay, so I don't see the slide. Slide is automatically coming, right?
Let me see if I can do that for you. I think they're on now.
Okay, so yeah, thank you, Cell Press team, to invite me here. It's a very exciting opportunity to discuss about the future of the memory. Today, I'd like to discuss about the briefly introduce the unique technology to help breaking the memory war, which is called the single crystal based monolithic 3D integration. So okay, let's go into the background of it. So let's briefly discuss about the memory war. So as you all know, these days, AI era, so the computing requirement substantially goes up, but due to the memory war, it's not catching up. We know, microprocessor in regime, we are doing pretty fast, memory and computing, and memory required for the cache is pretty quick. But in DRAM space, SSD space, it's not. The speed is not catching up with the speed in the microprocessor. That's why there is a memory war, and this memory war problem becoming much more severe because of the physical separation between the processing unit and memory unit. It is being connected through the wires, laterally side by side. Chip-to-chip communication is required. So there has to be substantial data movement and power consumption. Substantial, there will be RC delay, right? There's a substantial bottleneck here, physical bottleneck here as well. Then it's really time for us to think about how to mitigate this situation. And as time goes by, we require for the computing and data exchange between the memory and processing units much more substantial going along the way for the AI. So what should we do to this? So before talking about enhancing the communication between the processing unit and memory unit, we have to think about the way to enhance on-chip capacity, right? So in processing unit, we do have SRAM that can temporarily store the data right next to the logic, and it is fast. It is fast, but capacity is pretty low. It's a 60. Capacity is pretty low, even if it's faster. Then how can we mitigate this problem? How can we have much more a cache data storage, near the transistor? Then answer is, at the moment, is no, because we are already reaching to the scaling limit. The only way that you can have more than 10 gigabytes, the storage, you have to make a very, very big chip. But still, even if the chip is big, you can have very big storage right next to the logic, so which is good, but it's really big. So there's a limitation. DRAM, let's have a look at the DRAM. We are here at the B cap, there's the capacitors, and we have a bin line right next to each other, which is not area efficient. So these days we are moving on the V cap that can have the underlying transistor right below the capacitor, so we can save the space. Then still, you can but only do like a 6F to 4F scale. So it's not enough to enhance. Furthermore, then these days this kind of 3D DRAM has been discussed under the table, but in order for us to work more like a VCAD, we need to have like 15 layers of them. In order to go beyond them, we need to have hundreds of them. And it's practically, process is pretty complicated. So we have to think about something really, solving this problem. So that could be the monolithic 3D detection that I'm going to talk about later. So at the same time, when we talk about the off-chip bandwidth problem, between the memory and the processing unit, these days HBM does a great job to mitigate this problem, but it has to still leave with the memory work. But this can add more shutters between processing unit and memory unit. So this could be like 50 times more shutters between CPU and memory. This is a great solution because you can create a lot of passes, in between from the DRAM to the logic die. So we can create a lot of paths, so then we can add more shutters. So it can do the better job, by increasing the bandwidth. But still, there's a limitation. Memory is not broken. Then what do we do in the future, right? Then we have to take a look at the current limitation in HBM by using the TSV. Okay, we have to drill the hole through the TSV. Then once you drill the hole through the TSV, is around the 10 microns, and if there's a keep out zone, it's going to be like 30 microns. So we really sacrifice DRAM space. Also, there's a cooling challenge with DRAMs. Stacked DRAM is pretty thick with the wafer, and it's a stacking challenge as well. Then we are looking at my group and my collaborators looking at the way to make it much better by omitting the wafer between the device. If we omit the wafer, then we are able to create a nanometer pitch. So then this shatter problem, bandwidth problem, could be substantially mitigated. So you can do if you omit the wafer, you can do the block level connection and gate level connection and transistor level connection. So this is a very, very exciting opportunity. This could be done by transfer of a single crystal material. This could be done by growth of a single crystal material on the chip. This is quite exciting, but there's material challenges. You need to know how the single crystal based monolithic integration to mitigate all these problems. That is comes down to material problem. The reason we are able to find a way to grow single crystal channel materials straight on the chips. You can have a look at this paper later, and it requires material innovation to allocate the single crystal material right on the chip. And this is simple, kind of calculation that we did with Professor Sung Lim, used to be in Georgia Tech. He tried to, calculate if you can stack up the S-stream vertically, then compared to this 2D allocation, we can have a lot more bandwidth even using legacy nodes. So that is sort of like an exciting feature of monolithic 3D integration. So that's the direction they would like to bring in the table today. Thanks so much.
Thank you so much, Yuan. That was very interesting. Thank you for your insights. And now I would like to move on to Wei. Wei, if you can go ahead.
Okay, right. I think it's loading, so it just hopefully, yeah. All right, so mine is really short. I think Ramesh and Ji-Huang already gave a very nice intro. I will just quickly cover what I did and share some of my thoughts. So, all right. So I work on this memory called the resistive random access memory. Some people call them memristors, right? So the idea is on the left. So it's a very simple device, just has two wires crossing each other with a film in between. And when you apply voltage between the wires, you actually move atoms or ions between the two wires. So by doing that, you can change the resistance of the film. So you can get between high resistance to low resistance. So there's obviously a lot of interesting science going on. I will not bore you with that. So I've been working on with this type of memory since 2005. So this is one of the papers we showed prototypes. But as everything, there's a lot of challenges, right? So it's very useful to demonstrate a single device, show a small array. But then I think some of the topics we'll touch today is that how do we bring the emerging devices to the market, right? How do we make a real impact, as Ramesh has said? So that's actually a lot harder, right? So we have been working with companies, including my own startup, to try to scale this device, right? So that's bottom shown in the bottom. So there's I have a startup called Crossbar that was founded in 2010. So that's a 12-inch wafer. You can do that. But then the question is that, can you show enough benefits compared to today's memory? So that's even harder. So there's a saying, right? Obviously doing science is hard, right? Doing startup is hard. Doing hardware stuff is harder, right? That is the reason called it's called hardware, right? It's hard. But there's also another thing, like which I like a lot. So how do you make a small fortune in semiconductors? The answer is that you spend a big fortune. So it's really hard because there's a lot of challenges. Hopefully we'll touch some of the challenges we'll discuss today, and maybe some of the possible solutions. But this is really one of the areas we spend a lot of time on, a lot of other groups spend a lot of time on, because they can address some of the challenges both Ramesh and Ji Huang discussed earlier. So that's one memory research. We also work on the in-memory computing. I think Ramesh also mentioned, right? So instead of having a separate memory and logic, and we try to directly perform computing inside the memory, so that you get rid of the cost of moving data around, and also the both bandwidth and energy cost. So that's theoretically it's very good, right? So the idea is that you, for example, in the memristors, use the resistance to store data, then use the Ohm's law and Kirchhoff's current law to perform vector matrix multiplication. So again, you can build very nice prototypes and publish nice papers. But then the question again is, how do you do this very reliably and do it in a very large scale? So that's one direction. The other direction is that you can go beyond using this device to do digital computing. For example, just do vector matrix multiplication. You can use a different type of physics to do computing. This is also something Ramesh mentioned. So using physics to do computing, but change your equation, change your algorithm. So instead of just treating your weights and input vectors separately and do the multiplication, I perform the equivalent function. For example, if I'm doing a temporal analysis, I directly implement my temporal physics in the device. So that's using physics to do computing. So that may be one way to get around some of the more fundamental limits. So that's another area we spend a lot of time on. And to scale the system up, I also have another startup. Again, it's hard work, right? It's hardware, it's hard, and but we have been making very good progress and show that you can actually build scalable systems and design different system architecture and software to hopefully bring this system to real applications. So I'll end here, and I'll be very happy to answer questions in the discussion session.
Well, thank you so much. I think I'll particularly like your quote, hardware is hard. I think that's so true. Cool. And last but not least, I would like to ask Swan to come on board and share his deck.
Hello, I'm Simon Dada, and I'm professor of electrical and computer engineering at Georgia Tech. Very happy to be here on this panel. So some quick to set the stage. Already, what the previous speakers have explained. I have this plot explaining the memory landscape just for context setting, and the fundamental trade-off between access time, both for read and writing a memory, versus the density, which is directly related to the cost per bit. And you can clearly see that there is a strong hierarchy. It's been there for a while. And from all we have seen so far, this hierarchy is not going to change, at least in the near future, in the next decade or so. So at the very bottom, you have static random access memory, SRAM, that Ji-Won also mentioned. It's extremely fast, keeps up with the processor, but it has major scaling challenges, and the density is more in the range of megabyte. And there is a lot of ways to extend SRAM by making either a bigger wafer class die that he mentioned, and also with Vcache, which is essentially taking a memory chip and sticking it on top of the processor die using hybrid bonding. The next comes is the DRAM that's sitting outside the accelerator of the CPU, and which is dynamic random access memory. These are gigabyte class, and you're seeing right now a tremendous amount of demand for DRAM, both commodity DRAM as well as the high bandwidth memory that Jiwon also mentioned. And if anything, in the next couple of years, energy is one problem that Ramesh mentioned, but this memory is going to be access to memory, and capacity of memory is going to be the other major problem that we're seeing as we build up the AI infrastructure. So DRAM is sitting, and then after that, there is a big space when you get to more storage type memory, which is vertical NAND memory. This is the slowest of everything. You can see that the access speed is about milliseconds, but it also has the highest storage density. So, and it's non-volatile. So based on that, we get this so-called hierarchy. And as soon as you put this on the scale, you also start identifying there are gaps also. So one of the main focus of any emerging device, and in my case, my group works on ferroelectrics, as Ramesh mentioned, we have been trying to say whether any of the emerging memory classes that we're working on can fill one of these gaps, the gap between SRAM and DRAM. We look at a device called ferroelectric field effect transistor, where ferroelectric is integrated right within the gate stack of the transistor. And then the gap between DRAM and NAND, you can actually have, or more closer to DRAM, you can have a 1T, 1C ferroelectric random access memory. You can see that these structures are getting very complicated, that Jiwon also showed, because fundamentally memory has already gone towards 3D in the case of NAND, but in the case of DRAM also, it's moving in the Z direction of the third dimension. And we expect something similar to happen even with any alternatives between SRAM and DRAM. There is also a lot of exciting research coming out in architecting ferroelectrics for storage type of memory to replace NAND. And next slide, I will show you some of the work that's going on in the group, just to highlight the advancement, but also highlight some of the fundamental challenges, both at the science level as well as the engineering/technology level. And to me, these two things can go back and forth. So for example, if you're trying to replace SRAM, one of the things is that you're trying to design a memory which is logic voltage compatible. And that takes out a lot of emerging memory, because if you have to apply high voltage or high current, that sort of negates many of the benefit of that particular memory. Also, because it's closer to the processor, it has to be fast enough to keep up with the demands of the compute. Also, it's probably going to be accessed both for read and write operation very frequently. So it also has to have a lot of cycling endurance over the product lifetime. The next group of devices that are sitting in between DRAM and storage class is related to this 1T, 1C type of a structure. You can see it's a very dense memory cube in order to compete with DRAM. DRAM today, we are talking about a stack of DRAM, a 3D cube, or even the HBM that Jiwon showed in the range of tens of gigabyte. And once you go from a megabyte to a gigabyte class of memory, I think Wei was mentioning that it gets hard because of the statistics. And once you have to manage those statistics, meaning the distribution of the bits, then it becomes a very, very challenging problem, both from fundamental materials, device physics, as well as from the technology standpoint. So we have been building some of these type of devices as well in terms of stacking. So you choose the right materials that you can stack. It has to be bit cost scalable, meaning that you don't want to repeat the patterning at every stage. Otherwise, it's prohibitively expensive. So it's a lot of process integration as well as materials interplay, as well as understanding the reliability physics of these devices. Let me just switch gear. Also, there is a lot of action and happening on the compute side of things, not just the memory side of things. And what's shown here is this plot between energy efficiency, which is given by trillion operations per second. We like to call it TOPS, normalized to watt. that is the power that is dissipated or consumed. And on the x-axis, you have the raw performance. So on one hand, we need the raw performance. We can always trade off performance with energy efficiency, but that's not the point. We need the high performance to support these AI workloads, both for training and inference, as well as we want to hit that efficiency. So if you, this is a fairly busy plot, but I just want you to give you a sense of where the landscape is here, which is that at the very bottom, we have general purpose compute, the CPUs. And then but the advantage of CPUs is that their programmability, right? We can program these CPUs extremely well using high-level programming languages. The accelerator that came in about 5-6 years back and now has pretty much taken over the computing universe is the the graphics processing unit, or GPU, from NVIDIA. And you can see that they have almost an order of magnitude higher TOPS per watt, as well as they're hitting the tops as well. And after that, there is a lot of accelerator classes, and one of the well-known one, I would say, is Google TPU. Initially, it started as an internal project within Google, but now you can see that slowly it has made its way, or making its way, into the cloud ecosystem. So this is another success story of another class of accelerators that are providing even higher TOPS per watt. And the reason for that is it's becoming less programmable, less flexible, but it is also trading that off with more and more compute efficiency. So if you basically follow that trend in compute, then you're going to the next class of devices, which was mentioned also by Wei, both near memory processing, basically moving some of the processing into a base die that you can stick under, let's say, a DRAM. And memory companies are actually customizing this base die. So you're already seeing this happening and moving into commercial domain. The next part, which is now still in many startups, accelerators, university research labs are involved with, is called in-memory computing or in-memory processing. Within that, you can do it either digitally, which many people favor, or you can do it with analog, which are extremely fast, energy efficient, but has other challenges. So that's the class which is of devices that you can see that memory, we are actually using the traditional memory or any kind of emerging memory and trying to develop these compute accelerators. And last but not the least is what I think Ramesh mentioned, which is these new classes of materials, whether it's multiferroics or any material with ferroic order that you can architect into devices. And then if you try to just use them as simply as 0 or 1, maybe that's not that exciting. But if they have some interesting dynamics hidden within them, and you can go into what we in our group like to refer to as continuous time dynamical systems or neuromorphic dynamical systems. I know Wei works on this a little bit on the structured state space model-based dynamical systems. So we can actually leverage some of these internal dynamics and physics to create this next generation compute model. So I'm going to almost run out of time, but I just want to leave you with this some high-level descriptions of what we do. For example, a while back, this is almost like 5 years back, 6 years back, where we were looking at ferroelectric-based ternary content addressable memory array. It sounds like a memory, but it's very different from a regular memory in terms of that you can actually store patterns within this TCAM cell. And if there's a new pattern or new feature that you extract, let's say from an image comes in, then it can do a very fast parallel search, which is actually a computation. You're comparing two vectors means you're calculating some Hamming distance or cosine distance between the two vectors. And it has been used extensively in the case of high dimensional computing or HDC. And we were able to do that with extremely compact cells, leveraging the ferroelectric physics. The other example at the bottom below is related more to what Wei showed in terms of a crossbar array, except instead of a MRAM or a memristor, we are using a 3-terminal ferroelectric field effect transistor. And in this particular case, you're basically doing these accelerating input vector times a stored conductance matrix multiplication. It's called analog in-memory compute. You can store multiple bits even within these ferroelectric FinFET type devices. And in our case, we were looking at digital feature extraction from some streaming analog data to make smart sensors. One thing I want to leave with a word of caution is that even if the physics also works out, even if you're able to demonstrate a device, even if you're able to demonstrate an array with the peripherals, one of the things you also have to worry about is computational accuracy or precision. And this is when you look at the precision of compute, then you start realizing that you have to address for all the parasitics in this device. You have to look for all the noise. And even though from tops per watt or tops, everything looks great, then when you actually deploy it in real life, you see that that the precision is not just high enough to succeed commercially. So those are the kind of engineering, technological applications level challenges that again get fed back to the materials drawing board and the device physics drawing board. So that's sort of the message I want to leave you with. Thank you.
Thank you very much, Suman. I would like to ask all panelists to come back on camera so that we can start our discussion. And I think I will. Your last sentence, Suman, is I think a great springboard for starting this discussion, which is you've all mentioned that there are several challenges that we're facing on several fronts: the device physics front, the technology, the engineering of different device architecture, and ultimately the commercialization challenges. Because whatever we do has to be viable, has to offer benefits compared to what's already out there, and in the context of this ever-growing energy monster that requires thousandfold increase in energy efficiency. So. Given that we have limited time to discuss, I would like to basically throw you an open question, which is like out of in these three kind of fields of device physics, engineering, and commercialization, can each of you maybe tell us what you think the biggest challenge is, particularly for the technologies you're working on, but more generally, if you, so I give you sort of carte blanche, whether you want to start from the device physics or the more applied aspects, but basically what do you guys think we really need to solve next for these technologies to really make an impact, and quickly, given the pressing needs of the AI, making us consume ever more energy? Who would like to start?
I can quickly take a shot at this.
Please.
So if you look at emerging memories and take a quick look at the history, and we have resistive RAM, we have phase change memory, and we have spin transfer or MRAM, STT-MRAM. And if you look at these, where these technologies went, RAM is actually, if you're looking for a low cost, low capacity, IoT type devices, Internet of Things devices, then RAM is actually making its way. Okay, not what we thought before, but it's actually happening. If you look at STT-MRAM, we thought this is an extremely fast memory SRAM. That didn't happen. That being said, it's actually making its way into automotive for a completely different reason. It works at a high temperature, and it uses less number of lithography steps than eFlash, embedded flash memory. If you look at the phase change memory, that went into a gigabit class or gigabyte class memory, storage class memory. It was introduced, and then it was pulled back because the started scaling. So we have already three examples of emerging memories that have had different types of success. So if you look at the other new emerging memories, whether ferroelectrics that we're thinking about, or any other SOT, spin orbit torque, or any other new memories, I think what the lesson, at least for me, is keep pushing it. It may not end up exactly what you originally thought, but eventually the marketplace will figure it out in terms of where this technology is going to go. And it may not be quite what we originally thought, but the value proposition, still you just keep pushing on the value proposition and it will make it work. But I want to mention that going from kilobyte to megabyte to gigabyte and terabyte class memory, the challenges change completely. And that's why I think that we need to have also a very holistic sort of approach to looking. Memory is not a cell, it's the entire system. And if you look at today, memory companies are investing heavily in logic transistors. And the reason they're doing that is because of the I/O. And how do you move data back and forth? They're adding more logic functionality to the memory die in terms of hybrid bonding. So I think there's a lot of excitement. This landscape is evolving very fast. A lot of new things coming up, and we got to look at it holistically from that sense. It's not the past memory research anymore. It's a lot more exciting going forward.
Thank you, Suman. Who would like to go next?
So I think Shuman made some fantastic points, all of my colleagues. I think this particular business, all of the topics I mentioned, right? When you solve them, the world will be different. You remove CO2, that's a big deal. You go from carbon to hydrogen, that's a big deal. Similarly, in computing, it is a big deal for sure if we can solve all these problems. My biggest concern is, again, I'm now probably speaking like a professor, is that we need to have sustained investment. If you look at how we did Sunshot, the argument was that you take a problem area and you invest. Actually, the US government did a fantastic job there, DOE. Actually, it didn't put all the money in. But the biggest thing it did was to set a target. It said, go to 3 cents a kilowatt hour and the world will be different. Most people said, you guys are smoking weed. And we said, I don't think so. This is quite possible. So I think you have this sustained investment to solve a problem. Sunchart actually did it in 8 years, went to 3 cents a kilowatt hour, and our target was 10 years. I think we need some things like that in terms of bringing the focus. SRC did it, to be fair. The JUMP program that Shuman led, one of the teams and stuff, was meant for that. But this whole business has become so competitive globally that it's also getting very fragmented, very parochial. And that's probably not good for problem solving, but it's good for making money, I guess. So that would be my biggest, the challenge question. How do you solve these problems? You absolutely want to get the next generation, even my generation, to be going after these mission impossible kind of problems. It's very clear. Shuman said this, all of my colleagues said this, that the outcomes are actually not very obvious. So it's a completely open game. You just need to innovate, and see where it goes. Wei, Jiwan?
Yeah, definitely. Yeah, I think I fully agree with both Suman and Ramesh said, right? So there's a lot of time you start with one goal and you find something more different application. The memory market is very, very, obviously they are making a lot of money now because everybody needs more memory. AI is eating up all the memory, but it's very, very competitive, right? We already have 3D NAND, which have extremely low cost, very high density. We have DRAM. So all the memory companies are just focusing on making HBM, just getting NVIDIA to adopt their HBM, right? That's their focus. So then there's all these niche applications Suman mentioned, right? I feel like personally we should continue with material and device research because that will eventually lead to potentially better memory. But if you are looking at one area which say this is the most exciting area, I would say it's really the 3D memory, right? I think both Suman and Jiuhang already mentioned. How do you make really high density 3D memory that still give you the performance, right? So give you the read latency, give you the write endurance, give you the low read energy and the high bandwidth. So that will, and the high density. I think the density will be the biggest factor. So if you can get the density and then people can live with this and just accommodate it by moving by changing other architectural parameters. So if you can get the highest density integrated on the logic die, I think that will be the most interesting area. But it's really, it requires collective efforts from materials to devices to systems.
Yeah, so I'm the last one. So yeah, so I'm so much biased into these days M3D, monolithic 3D integration to make a nanometer pitch interconnect. That would be the ultimate solution. We all agree, I think, but it's a matter of material science right now. Even if, let's say, you do the monolithic 3D integration of polycrystalline-based capacitor, still you need to have a peripheral circuit that is run with a single crystal. Single crystal have to be stacked up to boost up the speed. Then do you know how to allocate a single crystal material right on the chip? That is a critical question to be answered, and material science becomes very, very important. And at the same time, in order for this complicated memory technology is successful to break the memory war, we need to have the environment that promote the collaboration between the material science and electrical engineer and computer scientist. So from the very bottom of it to all the way top system level and algorithm level has to be closely work together, but this is very challenging, very hard. So we really need to find some way to do so. Probably, as Ramesh mentioned, strong support from the government and industry to have them, closely discuss each other. And on top of that, we are established professor. Maybe our brain is already kind of frozen, but if we can educate students who can do the materials all the way to the algorithm development, if we set our educational goal for that, then future will be quite bright. I think that's kind of like things that I'm envisioning these days. I hope everyone agrees to this.
Thank you, everyone. And if I can maybe pick up on what you guys have been saying. So, Suman, would you say from what you were discussing earlier that it's a little bit it's not clear yet whether these new technologies that you guys are developing now will effectively disrupt the market in terms of replacing existing architectures, or they will end up more in a specialized niche, like you were saying. So if I get your message is it doesn't really matter if that's what ends up happening, because it's still kind of advancing aspect. If I misunderstood, please do let me know. Is that what you were saying?
Yes, I think that what I was trying to get to is that any technology has to map onto the application, and when we try to do that, multiple things come up, and so when you go translate the workload requirement, and workloads are changing too. I mean, even 4 years back, if you were talking about large language models or transformers and the amount of data we have to move things around, I would have told you no. I mean, I don't see that, but it is happening. It's happening extremely fast, and that is giving rise to a lot of changes on the technology side. So ideas of hybrid bonding has been around for a long time, and the people thought this is too expensive. You're not going to make a cube to yield, but it's yielding. People are paying. People said memory business is nobody will pay you anything more than a few cents for a bit. But it's happening. People are paying good money to buy memory. Suddenly, memory goes from a commodity to a luxury item, Louis Vuitton. So what I'm saying is that it's all these interplay between technology and that's setting the stage. What we need to do is the reason why Jiwan and Wei and Ramesh are all saying the same. We're all saying this kind of the same thing, is that that when you map the application, then you start realizing what your memory is really good for, what your technology is really good for. And that goes back to the fundamentals. So this idea that science is decoupled from engineering, I'm personally very opposed to this idea.
Amen. Amen, Suman. Absolutely.
so I think that
yeah.
Go ahead, Ramesh.
No, it's a continuum of states. I don't think we can separate out science.
Exactly.
Actually, what we learned from Sunshot was you can't even separate out the markets. There's a whole continuum from quantum mechanics to global markets.
Fortunately, in our case, we do have a market that is willing to pay. As we are seeing with the amount of capital that has been committed to AI infrastructure building. Right. So I'm hoping that this is the same thing that will happen to the energy, because the demand for energy is so much. That being said, so I think that you go back to the device physics, you go back to understanding. So the biggest challenge that I find in our research, and particularly working on memory, is reliability, variation. We take these things for granted. Oh, these are engineering problems. We kick the can down the road. Someone else will deal with variation. The quality engineering team. No, some of those variation reliability challenges are into the fundamental physics. The sooner we address that, even in a university lab with our researchers, that mindset that ultimately you got to deal with the statistics. That's probably the biggest message I want to.
Yeah. By the way, a couple of points on what Shimon said. Pick up. One is the nature of the markets. If you remember, I mentioned these 5 topics. 4 of them are in commodity markets, which means the margins are very small, which means new technologies. We saw that in solar. New technologies getting in and taking a market share is very difficult. The computing part of it is the only one where the margins can be very large. Look at NVIDIA and all of these companies, the margins can be large. So innovation has a huge role to play. Innovation at the physics level, circuit level, technology level, every level. That's a big plus point in this particular field compared to the others.
Oh, I think we lost Ramesh. Hopefully will join us back in a second. But while we wait, I guess one related to what you are saying right now, and Jiwon, what you mentioned earlier, do you think that we have the right environment for fostering collaborations between fundamental researchers in various disciplines, material science, physics, etc., computing science, but also the engineers that will have to put this, make this a reality, and the general kind of funding aspect. Ramesh is back. I don't know if you want to. Ramesh, are you okay? Sorry, you cut off for a moment. Do you want to?
No. I was just waiting to see this whole business of, do I really need to be perfect, or can we do imperfect computing and still get insights?
Yep. Anyone wants to follow up from there, or I can go back to my question to Jiwon? Okay, just to finish my question, it was from what you're all saying, collaboration is essential, and I was just wondering if you feel, particularly in the United States, because that's where you're all based, if you feel that that's something that is working well in terms of collaborations between different departments, but also different actors.
Yeah, so, okay, it is very hard to communicate, especially from me, material scientists, communicate with architecture guy. Very hard. And sometimes we try very hard to communicate, but still there's a gap. Then, it's vice versa. Architecture person really wants to know about the material innovation there, but when they're trying to talk to each other, with full of enthusiasm in the first place, we tried, but it's gonna be kind of fading away pretty quickly because we couldn't communicate each other very efficiently. So it requires some sort of like resilience. It's sort of like some pressure for us to discuss together, to educate each other, to make innovation. To do so, I think big pressure could be set by the funding that we got together. You know what I mean? So that kind of interdisciplinary team and funded by industry and government is super important for that. Then we are obligated to talk to each other. We keep on trying to break the barrier between us. Then it will truly, we would be able to make the progress, meaningful progress in it. So that's kind of the general view that I have, and also at the same time kind of limitation. So yeah, jump program is good, design is good. Still, if you can have some more opportunity and motivation to work close each other, that'll be great. That'll be great. Yeah.
Thank you. And we have a few minutes to go, but I would like maybe to take a couple of questions that came in from the audience. There's a few for Wei that are quite specific to what you're working on, Wei. So one is, what kind of applications do you see as viable for MVM applications with MRAM in memory computing? And can you ensure memory high temperature retention for long times with those applications?
Yeah. So depends on the device. Some devices really return data really well at high temperature. That's why they are used in some of the niche applications Suman was already mentioning. For compute, obviously, right now, if you use them to do VMM, it's because it takes a very long time to write. They have a limited endurance cycle, write endurance cycle. So they are better suited for so-called wait stationary. So you don't have to wait all the time. So if you do that, it's not compatible with transformers where you have inputs, the both matrix are changing all the time. So it's more suitable for like fully connected networks or like the old CNN. So it's very good for vision, but for transformer type, you really need memory that can be updated extremely fast. Some parts of the transformer can be used for that because in transformer, you also have some fully connected layers. They actually have a lot of weights. So it doesn't replace all the computations, but it replaces some of the data intensive but compute less intensive applications. So right now, I see most of them used in the edge, but not in the data center for RAM type of applications.
Thank
So
you
I
so much,
also want to point out, Ramesh mentioned, right, compute is not a commodity, it's a premium. But that's true in data centers. In the edge, people still, they are very cost conscious. But in the data centers, you can throw billions or hundreds of billions of dollars.
That's correct. Yeah, but overall, it's still a lot more flexible market. The margins are still larger than if you're selling electricity, which is solar's problem, that you had to come down to a parity point before you could actually get into the market. And so, yeah, the game is a little bit different in computing.
Cool. And I'll ask you one last question before we wrap up to anyone that wants to answer it. The question is, what is the outlook for phase change materials when compared to ferroelectric materials for neuromorphic computing?
Yeah, let me take a stab at it a little bit differently, okay? I mean, this is a generic answer. When we did the solar, there are many ways to capture the power of the sun. This is for the person who asked this question. Many ways to capture. One is you could convert it to electrons, or you could convert it to heat. They're all okay. So when we set up SunChart, we said, we actually don't care how you do it, as long as you meet certain specs. In our case, it was a cost spec. Similarly, coming back to phase change versus ferroelectrics and other approaches, MRAMs and whatever else, I think they all need to meet certain specs, performance specs, whether it's for logic or for memory or for AI, whatever it is. And as long as it does that, then you're in the game. I think you should go for it. There's huge amount of innovation that will happen, that is happening. And so I don't think you should change your game plan. But you need to be careful about, if it doesn't fit into the market, and if you're chasing that rabbit, then it will never proceed to the next level.
I just want to add to what Ramesh said. Speaking of phase change memory and ferroelectric RAM, I think that both have been demonstrated at the gigabyte level. So that's a good thing. I'm talking about 32 gigabit memory. Neither of them, phase change obviously had a longer development time. Ferroelectric is much more recent, exactly. So in that sense, they have both proven to be. The reason why PCM today is not used, it didn't see the commercial success, is there's endurance issues, and then you have to stack it deck by deck, and you have to repeat this patterning steps, and that became very prohibitive. And the endurance was a big challenge. How many times you can write into the cell. Ferroelectric has some advantages with that on that regard, if you use it purely as a capacitor. But that being said, I think the reliability physics is quite intricate. when you look at the fatigue and look at some of these imprint characteristics, time-dependent imprint characteristics. So again, the message is that it's not one or the other. You work on a technology. Typically, in my experience, it takes about 10 years just in the research lab. And you have to work at every piece of this puzzle before this is ready for any kind of prime time. And even when it goes to prime time, then the hyperscalers will decide if you're targeting that market, whether they're going to start replacing some of that DRAM, HBM with this new memory class. And that's the next level of challenge. So, and then that goes to the software that Jiwan was mentioning. The reason why it's so hard to talk to architects, and there are two types of architects: hardware architect, a little bit easier. Then there are software architects. They're optimizing something completely different. They're looking at memory as, can I look at all these heterogeneous memory as one unified memory? That when they're writing compilers and they're writing programs, they don't care exactly what the physics is. So I think that it's a challenge, but over time, as we work on a technology, we understand all the words, we abstract it out. And once we start abstracting it out, then they get much more interested. The good news is that there is a strong push and pull. We have to push from the materials device side, and the pull is there because the application needs it. One last point I want to mention in the context of the bigger scheme of compute today, particularly for cloud or these AI data centers, is that there are three pieces to this thing. Even if you look at when we are all using queries, we are using chatbots today, and there is a prefill stage, decode stage, and one could be very compute intensive. So you still need these very powerful GPUs that's doing computation, and you still need the memory access. So that's why the bandwidth and capacity is becoming, and latency is becoming such a. But there is also one piece, which is the networking piece. It's like thousands and thousands of GPUs all working together as one unified unit. So that's enabled by the networking. So I think that you can look at it as 1/3, 1/3, 1/3. If you just have progress in one area without the other, then that becomes the limitation. So we have to make progress in all these three areas, from networking, memory capacity, bandwidth, as well as logic performance. And we have to do all that while keeping this energy efficiency.
Exactly. That's right.
So that's why I'm very excited. And if there are any young people who are working in this area, hardware is I know it's hard, as Wei has mentioned multiple times, but it's also the most exciting place to be in. And right now, there's a huge demand for hardware engineers.
Yep.
Thank you, Suman. I think this is a great way to end our panel discussion, because we've reached the hour. I would like to sincerely thank all of our panelists for a great discussion. We've learned a lot from you, so thank you so much for giving us your time for this. I would also like to thank the audience for tuning in today and learn more about emerging memory tech. If you missed anything during the webinar, or you want to listen to it again, a recording will be available shortly and posted on cell.com. Also, for the audience, please take a few moments after the webinar to complete a brief survey that you will receive. Your comments really help us improve for our next events. So thank you, everyone, again, for all of your insights. And we hope to see you again to a future CellPress event. So thank you, everyone, and have a good rest of the day.
Thanks, guys. Very nice.
Thank you.
Thank you, Lisa. Yeah.
See you. Thank you.
Bye.